Hey everybody, welcome to another support video. This one is basically an answer document to correct an assignment I gave out. Study guide, square roots, power rules, scientific notation, and Pythagorean theorem. So if you want to learn about any of these skills, this was a good review kind of these concepts. So I'm just going to go through and correct with you guys. And if you're in my class, just correct. If you're not in my class and you happen to come across this video, then this is just how you do these types of skills. So I'm a little answer document here. Answer key. All right, that's funny. It's like a highlighted thing there. Okay. So simplify, write the value. So basically in these problems up here, you're trying to write the value of all of this. So you have to remember what you do here with exponents. So in any of these problems here, just to identify the different component parts, you have a base and you have an exponent, all right? And the bases I'm going to mark in blue, and those are the things that are being raised to the powers, okay? And then you've got the exponent, which is the little number in the upper right corner, and that's telling you how many times you're going to multiply the base by itself. So let me kind of just identify those as well for you. Okay, cool. And something that's kind of cool about this is you can see that the exponent only applies to directly what it's touching. So in this case, this is 3 to the third power. And that means that it's going to be 3 times 3 times 3. So you're going to multiply the base times itself 3 times. So this is just going to be 3 times 3 times 3. And let me see if I can change that up to green here. Perfect. So let's do blue actually. So this would be 3 times 3 times 3. And that's going to be 9 times 3, which is 27. Okay, so that's the answer there. I think they're doing some kind of cool highlight thing here, but I don't think I need that. Here you've got 2 to the fourth power. Now 2 to the fourth power is basically going to be 2 times 2 times 2 times 2. And of course, 2 times 2 times 2 times 2 is the same as 4 times 4, which is going to be 16. So this would be a value of 16. Now this one I highlighted the green 2 and I highlighted the blue 8 to show you that that negative that's there actually is its own thing, okay? So when you see a negative exponent, basically has nothing to do with whether the answer is positive or negative. That negative simply means the reciprocal of. So you're going to basically think of this, I hope, once you get used to it, as the reciprocal of 8 to the second power, okay? So you can think of that negative as the reciprocal of. So this is the reciprocal of 8 to the second power. Now, what does it mean to be the reciprocal? It just means that you flip it top to bottom. So if it's 8 over 1, it would be reciprocal to 1 over 8, okay? So in this situation here, this is basically just saying 1 over 8 to the second power. That's what it's really saying. And so 8 to the second power is 8 times itself. So that's going to be 64. So this is going to be 1 over 64. So it's basically the reciprocal of 8 squared. 8 squared is 64. The reciprocal of that would be 1 over 64. On this one, the exponent only applies directly to what it's touching. So you're raising the 6 to the 0 power. Anything to the 0 power is 1 other than 0. 0 to the 0 power is something where we wouldn't say it's 1. It's under debate. Some people say yes, some people say no. For us, we're going to say that 0 to the 0 power is not 1. But anything else to the 0 power is 1. So this is the same as actually negative 1. That negative just stays out in front, right? It's not part of what's being raised to the 0 power. If you had something like negative 6 in parentheses to the 0 power, that would be 1. But negative 6 to the 0 power is just negative 1. Because remember, the exponent only applies directly to what it's touching. Okay. All right, let's go to the next row here. So now at this point here, we're working on square roots. And remember, there are 2 roots of every value, of every square root. There's a positive root and a negative root. So when you have the square root of 196, this is basically saying what number times itself would equal 196. Now that would be 14, but not just positive 14, also negative 14. So the way you write this is plus or minus 14. So I'm going to kind of put this in blue here. So plus or minus 14. This one is the square root of 16. It means what number times itself equals 16. And that would be plus or minus 4 because 4 times 4 would work, and also negative 4 times negative 4 would work. The square root of 324 would be plus or minus 18. And just to double check that one, you can always put on a calculator and see, but the square root of 324 is 18. You're going to have to memorize, I would probably have 20 so that you get comfortable with these. And then the square root of 144 is going to be plus or minus 12. Okay. So now you guys have all the answers to this top section. And this is the skill we call simplify or write the value of or evaluate. In the second section here, we're going to apply our power rules to simplify the following monomials. Now, a monomial is a one-term expression. So all of these are monomials because they've got no addition or subtraction. Remember, terms are things that are added together. So if you only have one thing that's there, like one thing that's being added, then that is all one term. So these are all one terms, they're all multiplication or division. So they're called monomials, all right? But you can still simplify monomials using power rules and other various forms of mathematical properties, all right? So in this first problem here, we have 8 to the 4th times x to the 4th times x to the 3rd, okay? Now, the rule for when you're multiplying two powers that have the same base is you're going to add the exponents. And just to show you again how that works, if you have x to the 4th, that's x times x times x times x. Then you're going to multiply that by x to the 3rd, which is x times x times x. Well, what is that really worth? It's just 7x's times themselves, right? So this is going to be x to the 7th. So that's kind of where that rule comes from. But the idea of it, the shortcut is, whenever you are multiplying two powers that have the same base, you just add the exponents. All right, so let's go through and do that. So in this case, you're going to get x to the 4 plus 3. This will be x to the 7th, right? X to the 7th. All right, here you have 5 to the 2nd times 5 to the 3rd. So this is the same as 5 to the 2 plus 3, which is going to be 5 to the 5th. Here you have 4 to the 7th times 4 to the negative 2. This would be the same as 4 to the 7 plus negative 2, which is going to be 4 to the 5th. Okay? When you're doing the next row here, this is all about dividing powers that have the same base. The rule for dividing powers that have the same base is that you're going to subtract the exponents. Okay? And the reason for that is if you think about number 12, for example, this is like x to the 5th over x to the 1st, right? Well, what does that really mean? It means x times x times x times x times x all over x. Well, we know that anytime you have the same value on top and bottom, they're going to cancel each other out. So what you really have here is 4 x's times each other on top. Hence the answer being x to the 4th. The shortcut for this is to realize that this is dividing two powers that have the same base. So all you have to do is just subtract the exponents. So x to the 5 minus 1, x to the 4th. All right, now you know where that comes from if you forgot, and that might be helpful to you. Okay, when we're looking at the next problem here, is 4 to the 6th divided by 4 to the negative 2. So that's going to be the same as 4 to the 6 take away negative 2, which is 4 to the 6 plus 2, which is 4 to the 8. Here you have 5 to the 7th divided by 5 to the 3rd. That's the same as 5 to the 7 minus 3, which is 5 to the 4th. When you're doing this one, this is a row that we're talking about raising a power to a power. When you're raising a power to a power, you're going to multiply the exponents in that case. And the reason is pretty simple, right? If you have x squared to the 4th power, what that basically means is x squared times x squared times x squared times x squared, which is, as you know, x times 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 x. So that's 8 x's times each other, right? So that's how we know that this rule works, right? X to the 2nd raised to the 4th power is going to be the same as x to the 2 times 4, which is x to the 8th, right? And so now hopefully you see where that comes from. You remind yourself of where the rule comes from. It makes it easier to apply that rule in the future. So when you're raising a power to a power, you're just going to multiply the exponent in that case. All right, and then here's y to the 2nd raised to the 7th. That's y to the 2 times 7, which is y to the 14th. Here you have 2 to the 4th raised to the 3rd. That's 2 to the 4 times 3, which is going to be 2 to the 12th. Now you can leave it like this because I asked it for the answers to be in power notation. And power notation means you can leave the value without its actual numerical value, but just in shorthand notation where you've indicated what the power is. So this is x to the 8th, this is y to the 14th, this is 2 to the 12th. Could we figure out what 2 to the 12th is worth? Of course we could. 2 times itself 12 times. But we don't need to because it says it's okay to leave it in power notation. Now, in appropriate power notation, we don't want to have the exponents being negative, so we want to make sure that it's only positive exponents. So as long as you have the answer with positive exponents, it's in power notation and we're happy with it. Okay, for number 18, this is a product being raised to a power. The rule for this one is that you're going to raise each factor to that power. So when you're raising a product of ABC to the fifth power, that's the same as A to the fifth times B to the fifth times C to the fifth. Okay? Here you're raising a quotient to a power. It's the same as raising the numerator of that power and the denominator of that power. So this would be the same as A to the second over B to the second. Here you've got that reciprocal of again, right? Remember that little negative meaning reciprocal of? So this is the reciprocal of x over y to the third. Well, what does that mean? Well, the reciprocal means flip it top to bottom. So this is the same as basically saying y over x to the third. Well, y over x to the third would be y to the third over x to the third. And that's your answer. On this one, let me put that back in blue, actually. Might as well call our answers in blue. So this is going to be y to the third over x to the third. There you go. All right, for this one here, you're raising a product to a power. So you raise each factor to that power. So this is 2 to the fourth power times x to the fourth power. Now it says you can leave it in power notation, so you could leave it just like that. That is acceptable. If you wanted to, you could also figure out what the value of 2 to the fourth is, which is 16, and write it as 16x to the fourth. Either way, it's an acceptable answer. On the next one here, we got to remember that the negative on the exponent simply means the reciprocal of. So you're going to flip this top to bottom. So I'm going to do the steps to this problem over here. So I'm going to do like number 22, so you can see kind of the process for this one. All right. The negative exponent simply means reciprocal of, so flip it top to bottom. So really this is the same as y to the third over x squared, all raised to the positive 5. So that's what we call resolving your negative on the exponent. So you just flip it and then make the exponent positive. And then now we're going to raise this quotient to the power of 5, which means you're going to raise each factor to that power, or sorry, numerator and denominator to that power. This would be y to the third raised to the fifth, all over x to the second raised to the fifth. And then you got to remember that when you raise a power to a power, you multiply the exponents. So your final answer here would simply be y to the 15th all over x to the 10th. Now in the next problem, anything that's raised to the 0 power is going to be 0 other than, sorry, is going to be 1 other than 0. So in this situation, no matter how complicated this thing is, everything that you see there is the base, and the exponent is 0. So that 0 applies to all of that, right? Remember, when you have a product, each factor gets raised to that power. So all of this is being raised to 0, which basically means the whole thing is worth 1. So the answer for this is very simple, 1. For this one, we're going to approximate roots. Here's my strategy for approximating roots. I like to look at the irrational root and figure out what the closest perfect square below it and above it are. Below this one would be 25, and above that one would be 36. So that means the square root of 32 falls somewhere between the square root of 25 and the square root of 26. That means it's going to have a value somewhere between 5 and 6. If you had to make a quick approximation, you'd say it's closer to 6 than 5, but a little bit less. Now, a better approximation would be start with the lower value, 5. It's got to be between 5 and 6, so start with 5. And then I want you to create a fraction here by doing this little step here, where you try to figure out and map out the journey. So going from 25 to 36, how far has this already traveled? Well, from 25 to 32, that becomes your numerator, 7. And how far does it have to travel? And that would be your denominator, and in this case, that would be from 25 to 36, which is going to be 11. So I think a really good approximation here would be 5 and 7/11. All right? And just to prove to you that that works, if you were to do on a calculator the square root of 32 square root, you can see that that's 5.66. And then if you do the fraction 7/11, it'll get very close to 6/600. Let's see how close it is. 7 out of 11. 64. So it's off by 200ths, basically. So a pretty good approximation. All right. When we're simplifying a irrational root like this, what it basically means is you're going to try to separate out the rational part from the irrational part. So first thing you have to understand is that when you are working with something like square root of 100, okay? 1 second, guys. When you're working with something like square root of 100, okay? We all know that square root of 100 is 10. I'm going to prove to you some things that you can do with this. We can write square root of 100 as the square root of 25 times 4, right? Now, I want to show you that you can then separate it into individual root factors. So you can say the square root of the product of 25 and 4 is the same as the square root of 25 and the square root of 4. And here's the proof. What is the square root of 25? 5. What is the square root of 4? 2. And isn't 5 times 2 still 10? So when you have a product underneath a radical sign, you can actually separate it out into two radicals times each other with each of the factors of that product. Okay, so that's pretty cool. So the fact that you can do that lets you do something called simplification. So we can simplify a irrational root by pulling out all the perfect square factors from underneath the radical. And let's do that. So if I have a square root of 32, I have to ask myself, what perfect square factors are factors of 32? Well, you think about your perfect squares, 1, 4, 9, 16, 25. It looks to me like 16 is a good one, right? So you could rewrite this as the square root of 16 times the square root of 2. Well, what is the square root of 16? The square root of 16 is quite simply 4. So this is 4 square roots of 2. And that is the way you write this in simplest form. In other words, you have the rational part, the rational value, 4, times the irrational part, which is the square root of 2. You separate it into the product of two factors, one being rational, one being irrational. So that's kind of the idea behind it. So you're going to pull out the rational number, and that's one factor, and you're going to leave the irrational number as its own reduced, simplified root. That is the irrational root. So basically look for perfect square factors that you can pull out, and then rewrite it as the product of the rational times the irrational. Let's take a look at the next one. The next one is 128. So if we do our approximation strategy here, this one below it is going to be 121, which is 11. The one above it is going to be 125, 144, which is 12. So this is somewhere between 11 and 12, closer to 11. And then if we want to do a better approximation, we start with 11, and then we realize that the amount of journey that's already occurred is from 121 to 128, which is 7. And then the total journey that has to occur is from 121 to 144, which would be 23. So 11 and 7/23 is a pretty good approximation of the square root of 128. Now here's the square root of 128, 128 square root. You guys can see it's 11.31. And so 0.31 is probably very close to 7/23. Let's see what 7/23 is. 0.30. Okay, but very close to 0.31. That's off by about 100. Not bad. When we simplify the root, you're going to do, once again, you're going to pull out the rational part of the root. So you have square root of 128. That's once again a multiple that we could use 4, we could use 16, but we can actually go bigger here. We can say that 25 is 5 times 5, 6 times 6 is 36, and then 7 times 7 is 49, and 8 times 8 is 64. Now, when we look at 64, it works with 128. So you could say this is the square root of 64 times the square root of 2. Hence, this is going to be 8 times the square root of 2. So this is 8 times the square root of 2 in simplest form. If you were someone who pulled out, let's say, a value that was not as big as 64, like let's say you looked at 128 as an experiment here, an alternate way of doing it, and you're like, you know what, I'm just going to pull out 2 here first. And like, let's say you saw that 4 goes into it, right? So maybe you thought, okay, 4 times something. Well, 4 times what? Well, 4 times 3 is 12, and then there's 8, so 32, right? So you got 32 left over inside. But then you can break the 32 into 4 and 8, and then you can break the 8 into 4 and 2. So you can kind of keep breaking it down. Now, when you do that, what you notice is you get all these basically rational bits here, right? That can multiply together. And the square root of 4 is 2, square root of 4 is 2, square root of 4 is 2. So it's 2 times 2 times 2 times the square root of 2. The only thing that's the irrational bit is the square root of 2, right? Well, what's 2 times 2 times 2? 8. So you'll notice that no matter how you break it down, no matter how you notice your factors, you still end up with the same answer, where you're going to get 8 times the square root of 2. Because the largest perfect square factor you can pull out is 64, but if you didn't recognize that and you pulled 4 out, you can pull 4 out 3 times, right? 4, 4, and 4. and that would be 2 times 2 times 2, or 8. So you could write this as 8 times the square root of 2, no matter how you started to factor 128. As long as you're pulling out one of these perfect square factors, you'd eventually get the right answer. But I think the easiest way is to pull out the largest one if you recognize it, right? And then we go down to here, you got some Pythagorean theorem here. So this is find the missing side of the right triangle. So some of these are really, really easy. I told you guys to memorize some right triangles. So here are some known right triangles that you want to remember. First one is 3, 4, 5. So any triangle that has legs of 3 and 4 will have a hypotenuse of 5, or anything similar to that. Okay? Another one that you want to memorize is 5, 12, 13. So if you have legs of 5 and 12, the hypotenuse will be 13, or anything similar to that. The other one that I want you to memorize is 7, 24, 25. If you have legs of 7 and 24, the hypotenuse will be 25, or anything similar to that triangle. And then another one will be 8, 6, 15, 17. If you have legs of 8 and 15, then the hypotenuse will be similar to 17, right? So anything similar to this will work. That's a right triangle. And then the last one is an isosceles right triangle, which is going to be x, x, and then x times the square root of 2. So when you have legs that are the same, x and x, then just multiply them by the square root of 2 to get the hypotenuse. These are known right triangles. I would recommend that you guys memorize those. So I'm going to write known right triangles right there. And you want to memorize these, right? So memorize these. Okay, now how can we use these things to help us? Well, 9, 12, something. I'm noticing, I hope you guys are noticing, you can divide both of these by 3, right? So isn't this basically a 3, 4, 5 right triangle? It's just that it's been enlarged by a scale factor of 3. 3 times 3 is 9, 4 times 3 is 12, and 5 times 3 is 15. So the answer here is just 15 units. On this one, maybe you recognize you can double these. And if you double these, you get what? 21, and double 37.5 would be 15 plus 60, so 75, right? Now, when I'm looking at 21 and 75, I can see that I can divide both of those by 3, and I would get 7 and 25. You guys notice that? Well, guess what? 7 something 25. Isn't that right here? 7, 24, 25. So I know this is going to be a 7, 24, 25 right triangle. But what's the scale factor? Well, how do you get from 7 to 10.5? Well, it looks to me like it's going to be 1.5 times 7. How do you get from from 25, I should say, to 37.5? Looks like it's going to be 1.5 times 25. So it looks like the scale factor here is 1.5. So what's 1.5 times 24? Well, it's 24 plus half of 24, so 24 plus 12, which is going to be the answer, which is 36. So you could have used your known right triangles to solve that and put 36 there, right? If you were someone who didn't know how to do that, you can always do a squared plus b squared equals c squared. So this is what this would look like. You'd have one leg, this is A, okay? This is C, by the way, and this is your other leg, B, right? So we have A, we have C, we just don't have B. So you'd have a squared plus b squared equals c squared. So it would be, in this case, let me write it all up for you guys. A squared would be 10.5. You're going to square that. B squared is the unknown, and that's equal to c squared, which is 37.5 squared. And then you just do it out on calculator. So you go, all right, we got this. 10.5 squared is going to be 110.25. So that would be 110.25. Let me see if I can minimize that. There we go. 110.25 plus b squared is equal to, and then over here you've got 37.5 squared, so 37.5 to the second power, which is 1406.25. So 1406.25. Write that in here. Well, let's see if this will show up a little better. It looks like it's not showing up the way I want. That's funny. 1406.25. And then what you're going to do here is you're going to just solve. For some reason, my cursor is not showing up. Give me a little pause here so I can fix this for us. All right, I think I got the cursor thing fixed. We'll see. Anyways, so in this case, you're going to get that. Then you're going to I guess I didn't get it fixed. No. You're going to subtract 110.25 from both sides. And you're going to get b squared is equal to whatever that is. So you got basically 1406.25, and you're going to take away 110.25 from that. You're going to get 1296. So now we know that that's going to be equal to 1296. That's 1296. Let's see if I can. 1296. And then you're going to have to take the square root of both sides to solve. So the square root of both sides. And the square root of 1296 is going to be 36. If you had a calculator, of course, you would know that. You won't have it memorized. But 1296 square root is going to be 36. Okay. So anyways, you can do it with Pythagorean theorem. Obviously, it's easier if you memorize your right triangles and solve with that method. All right, let's go into your scientific notation. So scientific notation here, I'm going to kind of change this to a focus tool, see if it helps the cursor showing up properly. So kind of doesn't work that great. All right, never mind. I'm just going to go back to classic. All right, so in this situation here, what you're going to do is you're going to recognize that in scientific notation, if your power of 10 is positive, that means you're going to move the decimal place to the right. So in scientific notation, when you see a positive power of 10, you're going to move the decimal place to the right when you see that. So I'm having a hard time with this cursor, so I'm trying to find a way to make it work better, but it's just disappearing on me all the time. Anyways, you're going to move to the right. And so you're going to move this 4 places to the right. So in this case, it's going to be past the 6 and the 5, and then 2 more places. So your answer here is going to be, if I can actually set this up, let's see. All right, I think it's working. So, all right. So, anyways, when you're working with this one, you're going to move it 4 places to the right. So you take the decimal and move it 4 places to the right, because really what this is saying is 4.65 times 100,000. Right? Is it 100,000? 1 with 4 zeros times 10,000. So this would be 4.65 10,000s. So it's going to be 4 times 10,000, which is 40,000. And 0.65 times 10,000, which is 6,500. So it would really be 46,500, right? But the shortcut to doing all that is just to realize that when you see a power of 10 to the 4th, you're going to basically move the decimal place 4 places to the right. So you're going to go past the 6 and the 5, and then 2 more places. So you just write 465, and then there's 2 placeholder zeros you have to go more, because that'll go 4 places from where it is currently. And then that's the answer, 46,500. When you are working with a power of 10 that is negative exponent, it means you're dividing by that. This is dividing by 1,000 basically, right? So timesing by 10 to the negative 3 is the same as multiplying by 1 over 10 to the 3rd, which is the same as dividing by 1,000. So really you're going to move the decimal place to not 3 to the right, but 3 to the left. So when you move it past the 6 and then 2 more places, so it's going to be 0.0067 or 0.0067. Now there's a cool shortcut that happens here that I want you guys to see, and that's pretty nifty. It's a nice little shortcut whenever you have a negative exponent in scientific notation. Notice that when you have 10 to the negative 3, it just means you're going to have 3 zeros in front with the decimal after the first. Pretty cool, right? That doesn't work when you're expanding out with a positive exponent, but it does work really well when you have the negative exponent on the power of 10. When you guys are doing number 30 and 31, you're writing these in scientific notation. You just have to locate where the decimal is going to go. So you want the lead digit to be in the ones place. So you want the decimal to be right here between the 6 and the 8. So in this case, you're moving it basically between 6 and 8. How far are you going to move it? You're moving it 1, 2, 3, 4, 5, 6 places. So you're going to write 6.8 times 10 to the, now we know it's going to be 6 here, right? But is it going to be positive or negative? Well, is this real number small or big? Small, so it's going to be a negative exponent, right? And then you can always test it, right? If you were to look at this, right, the negative 6 means you're going to have 6 zeros in front with the decimal after the first. 1, 2, 3, 4, 5, 6 with the decimal after the first. Perfect. And then on this one here, you want the lead value to be in the ones place. So you can move it 1, 2, 3, 4 places. So this is going to be 8.63 times 10 to the 4th. And why is it not negative 4? Because this is a large number, right? So you're really multiplying by 10 to the 4th. It's going to make it bigger and expand back out to its full size. So think about it. Shortcut it in your mind. Does it work? Well, if it times by 10 to the fourth, I'm moving it 4 to the right. Once, twice, and then 2 more. So watch. Once, twice, and then 2 more. It works perfectly. All right, so you just want to double check to make sure your values all match. And that's how you do this page. Hopefully that makes sense and everyone understands how to do it.